Okay, so now we're going to pick up on the next topic related to the integrated rate law, which is the concept of half-life of a reaction. So half-life is defined as the time required for one half of a reactant amount to be consumed. So when you have succeeding half-life, half of the remaining concentration of the reactant that you start with is consumed. So here's an example. So if you start with A naught as your beginning quantity, after first half-life, and it has a symbol of T1 half, you're going to have half of that starting quantity. You can go through another half-life, which we would call the second half-life, or the second T1 half, and you're going to have half of what you're starting with, which is A naught over 4. And if you do one more of this, third half-life, then you will have yet another half taken away, so it will be A naught over 8. Now, half-life is a really useful concept and number to look at because it immediately tells us how fast or how slow a reaction is. So here are some examples of them. Some of them are relatively short and some of them are really, really long. As you can see, for something like uranium-238, it takes 4 billion years for it to decay half of its starting quantity. So this is the reason why there's some concerns about using nuclear power, because the waste that is still radioactive will take a long time to decay. Now, we also have reactions that have much shorter half-life. They are shown here. Look at this particular reaction right here, which is just the dissociation of weak acid in this particular case, and you see that it has a half-life of less than a microsecond. Let me now show you how to get the half-life equation for each of the reaction order that we've discussed so far, which is the 0th order, the 1st order, and the 2nd order. The way you're going to do this is start with the integrated rate law for that specific order. So for the 0th order equation, we know that the equation itself is concentration of A equals to negative KT plus concentration of A naught. At T equals to T1 half, A concentration should be equal to half of A naught. And that's what we said earlier. So what we'll do is we'll just substitute that back into the integrated rate law expression. So we'll say A naught over 2 is equal to negative K. Now this is T1 half plus A naught. And then once you have that, you just need to rearrange the expression so you are solving for T1 half. So you can see that if you bring the A naught to the other side, you get negative half A naught. And then bring the K to the other side, you will be dividing by negative K. So the final expression will be A naught over 2K. That would be the half-life expression for a 0th order reaction. And you can see that I had also written it right here for you. There's actually an assignment for you in lab where you have to derive the expression for the half-life of the 1st order reaction. In the end, you should get that answer that's just highlighted. T1 half equals 0.693 over K. Now for the 2nd order, again, we start with the integrated rate law, which looks like this. When T is equal to T1 half, the concentration of A is equal to A naught over 2. So that's what I just substituted there. And of course, this whole expression right here is the same as 2 over A naught. And then if you bring this to the other side, that becomes minus 1 over A naught. And then if you bring the K to the other side, now you're dividing by K, and that whole expression is equal to T1 half. So if we simplify, then 1 over A naught times K. And so that would be your 2nd order half-life expression. You should have all those 3 equations in your head as you're going through half-life type problem, okay? What we want to do now is just use this equation to help us answer some of the questions related to integrated rate law, rate of reactions, and half-life. So here's the question that was in the lecture note. It says the half-life of a reaction of compound A to give compounds D and E. Reaction looks something like this. A goes to D plus E. They tell you the half-life is 8.5 minutes when the initial concentration of A is 0.15 molar. How long will it take for the concentration to drop to 0.03 molar if you're asked to consider 2 different situations here, if the reaction is 1st order and if the reaction is 2nd order? Now, the question is asking for time, so keep in mind that if you want time, you're going to have to use the integrated rate law. Remember that the differential rate law doesn't really allow you to calculate time. It allows you to calculate rate, right? So if we want to find time, we're going to need to find the integrated rate law that applies to our situation. Before we can find time, we're going to have to solve for the rate constant first. And to get the rate constant, since we're told something about half-life, we could use our half-life equation. We're going to have to use the correct half-life equation. First order one would be this one right here, which is T1/2 equals ln of 2 over k. You might have seen it earlier written as 0.693. That's the same as ln of 2. And the second order one is the one shown right here, which is T1/2 equals 1 over k times a naught. So we're going to start with our first order equation. So to get the rate constant, I'm going to use my half-life. And so the equation for the half-life is T1/2 equals ln 2 over k. So that means that k is going to be equal to ln 2 over T1/2. I have both of those numbers in my problem, so I'm just going to substitute that in and find that my rate constant is equal to 8.15 times 10 to the minus 2 per minute. Once I have that, I substitute it back into the integrated rate law to solve for time. I have these two numbers right here, the a and the a naught. I also have the rate constant, and substituting those in should give me 19.7 minutes for the answer if the reaction is first order. Now all we need to do for the other question is to use the second order half-life. So here, going through the same step, first we find the rate constant. So here I'm using the half-life equations for the second order. I rearrange it to solve for rate constant. I have values of both half-life and initial concentration, so that allows me to find the rate constant to be that number, 0.784. And then I go to the second order integrated rate law, rearrange it to solve for time, and substitute all the numbers I have, including the rate constant that I just calculated. And then so my final answer should be 34.0 minutes. Let's now summarize all the information that we learned so far about the two different types of rate laws and rate of reaction. Okay, so the first thing I want to emphasize is that we can calculate the rate of a reaction if we're given a rate law equation where it says rate is equal to k times concentration of A to a certain order and B to another order. If we have those rate constant and order values filled in, then all we need to do to calculate rate is just to plug in whatever concentration values we're given. What happens when you don't have the rate law? Well, there's two methods that we talked about very early on, which is first we can draw a tangent line to a concentration versus time curve, and then the slope of that tangent line would be our rate. Alternatively, we can use this expression, negative delta concentration of reactant over delta T, and calculate your rate. Now, what about order of a reaction? You've seen that in a lot of these questions, knowing the correct order really matters because there's different equations for different order. You're going to need to use one of the following methods to help you determine order. The first one is the method of initial rate. To do that, you're going to have the experimental data, and the experimental data have to have rate at different initial concentrations. So it's kind of a very special type of data. Another way is to check the unit of K. Remember that different rate constants unit corresponds to different order. So if you're given the rate constant, check the unit, see if it's 0 first or second, and then you can go ahead and solve the problem. Another one that we talked about that's a little harder is to graph the data. So if you're given concentration versus time data, if you graph it three different ways according to the 0th, the first, or the second, then you can see which of the graph actually fits. Whichever one fits, that's your order. The last thing we can look at that's not so obvious is the pattern of consecutive half-lives. So for this, I'm going to go back to those half-life equations. Take a look at this equation right here for first order half-life. Notice that the expression of half-life is just a number divided by a constant. So what that means, if you go from first, second, third half-life, right, like this here, as your reaction progresses, the half-life doesn't change. So if somebody tells you that, hey, my half-life is 20 minutes every time, that immediately tells you that that's a first order reaction. Now, if you look at the other two reactions, 0th and second order, notice that it's dependent on initial concentration, but it depends in opposite ways. For the 0th order, the half-life is directly related to the concentration. So if you're running a reaction, of course, the reactant concentration is going to drop. So therefore, your half-life is actually going to get shorter and shorter and shorter. So the first, the second, and the third half-life would get shorter and shorter. Whereas for the second order reaction, it's the opposite. It's inversely related to the initial concentration. So as you consume your reactant, your half-life gets longer. You're given a pattern where it says, my first half-life is 10 minutes, my second half-life is 20 minutes, my third half-life is 40 minutes, then you know that that must be a second order reaction. So that's what I mean here by check the pattern of consecutive half-life. All right, another important number that we look for is the rate constant. And there's, again, several ways to find this information. The first is to use the method of initial rates once you find your order. For the graphical analysis method, where you graph the concentration versus time data. Then you can find K using the slope. Remember that for the 0th and the first order plot, the negative of the slope is your rate constant, whereas for the second order, the slope itself is your rate constant. You can also use half-life to find rate constant. Notice that all the 3 different equations of half-life shows how they are related to rate constant. So rearranging the equation to solve for rate constant will give you that number. The last question that we've tackled in prior lectures is just how to calculate reactant concentration at different times. To solve for these type of questions, you're going to use the appropriate integrated rate law, which means that you're going to need to know the order. And so I'm going to go back here to one of these methods to figure out which one will help you figure out the order of that specific reaction.